Industry Economics Research Institute as a researcher, and from the associate researcher to the research manager, okay, from the 1983 to 1995, okay. He got an excellent young person prize in 1989, and then excellent inventor award, many award, and recently, okay, from in the year of the 2021 and the year of the 2024, he got the both Future Tech Award recently. Okay. Besides, Professor Liu, because he done lots of the practical research work, so he not only published the paper, more than 600 publications in the international important journal, and also got the total citation more than 35,000, and with H index is actually 95. And more importantly, he had more than 200 patents. Okay. The goal of Professor Liu's research career is to prepare to be illuminated by cutting-edge research that's lighting up the future. So today he is going to give us the talk about the light conversion materials in the leading future. Okay. Please give a warm welcome to Professor Liu.
Before I start, I would like to express my thanks to Professor Su and Chairman Lin's invitation. So then, good afternoon. Good afternoon.
Good afternoon.
Okay. So then, today I'm going to give you a talk based on the light conversion material leading future. So you know, GPT is very now welcomed by many people. Okay, you guys probably already make a practice. Today I'm also going to show you. So this one also drawn by ChatGPT, and also this title also revised by ChatGPT. So then I would like to advise you first. So please go to try ChatGPT. Then that will make your study more easier and more beautiful. Okay. So then our lab called Materials Chemistry Laboratory belong to Department of Chemistry, National Taiwan University. So this is a logo of my lab. So it's based on the cubic. So you know cubic is the simplest union cell of all the solid state materials. Okay? Then this one is an extension to 3 dimensions. So it means in our lab we use just like a kit, play Lego. Okay, so if you use Lego, you can assemble to different kind of material, different kind of function material like train, like rubber, anything you want. So then you can call our lab as a Lego lab as well. Okay, so then roughly my lab is working on the light conversion materials. So first, you see your mobile phone. So if you see your mobile phone, so you can see the white light part. White light, how can you get white light? So if you see that white light LED, they have a blue LED plus phosphorus. Okay, so you see the yellow color, so that is a yellow phosphorus. So if this yellow phosphorus, you excite by the blue LED to the yellow phosphorus, the phosphorus will emit the yellow light. By mixing with the yellow light and also the blue light from LED, so you can get a white light. So it means in our lab, we make inorganic phosphor. That is our first material. So other than this, we also make quantum dots. So phosphor and quantum dots, we are working on light conversion material. So that means we use the LED blue light to excite the phosphor or quantum dot. We can get another visible light. So we call light conversion material. It's our first target for light transition. Okay, so obviously this one is in the application of optoelectronics. Okay, so then the second one is light conversion to energy. So in our lab we have catalysts. We can solder the solar light into water. into our catalyst, we can convert water split into hydrogen and oxygen. Hydrogen can be as a source for the fuel cell. So that means we use a solar light, we can generate green hydrogen. That green hydrogen can as a source for fuel cell. So that means light conversion to energy or electricity. Okay, that's our second topic on this. So after you got energy, then you probably need to store this kind of energy. Then you need to have a battery. Okay? Once you have battery, that will be explosive, dangerous. So our lab developed a solid-state battery. So that means it's quite safe of solid-state battery. But this kind of battery cannot make a longer distance. Then, because too heavy, you have cathode material. Then we further develop into this, remove this cathode material, we put an air in. So that's so-called metal air battery. So then you can very light battery for the future. So for this one, we just make a light conversion to energy. So that is the work on water splitting, fuel cell, solid-state battery, metal air battery for energy application. So this is our second working target. So the third one is the light conversion to heat. So if you have mouth cancer, okay, for example, you eat betel nuts, you are easy to get a mouth cancer. Then we put the nanoparticle, like a gold nanoparticle, into the cancer cell. Then we excite by infrared. That infrared can absorb the energy, generate or transfer to heat. That heat can kill the cancer cell. So we call light conversion heat. Then can use for the biomedical applications. Not only for the heat, but also for active oxygen. That's so-called thermodynamic theory. That's also included in this study. So with this, you can see light conversion to light for optoelectronic material. That's including the phosphor and the quantum dots. For the second one, light conversion to energy. So we develop material for water splitting, fuel cell, solid-state battery, metal air battery. That's for the energy application. For light conversion to heat or active oxygen, so we use a nanomaterial. That's for biomedical application. Okay. For this one is a so-called light conversion material into three different kind of categories. And then the core technology of my group set it up 30 years ago in the year of 1995 when I moved to National Taiwan University. This year is my 30 years to stay in this university. For core technology in my group, including three parts. So the first one is the formulation and the synthesis. So formulation is important because that is the heart of the material. So we are based on inorganic material, so formulation is the first one. Once you have formulation, then you need a synthesizer. So synthesis technology is also one of our targets. So core technology is the formulation and the synthesis. So once you got the material, then you need to analysis it. So that's including XRD and TEM, SEM, or electronic part by using a single chron. So analysis is our second technology. So the third one is the application. So anything we are focused on application. So for our study, we usually will cooperate with industry or the research institute. We ask them what you want. What is your problem you want us to help you to solve it? Once we have that, we think, oh, that's based on our technology. Then we set up our goal to do that. So that is the three core technology in my group: formulation and the synthesis, analysis, and the applications. Okay? Once you have these three core technology, that means you can apply in three different fields. So that is light conversion to light. That's for optoelectronic material. So second one is light conversion to electricity. So that is the energy storage material. The third one is the light conversion to heat. That's can apply nanomaterial for biomedical applications. So as I told, everything unchanged is the core technology. core technology is your ability, intrinsic ability. But based on this intrinsic ability, then you are okay to make a change for this kind of things. So then you see we worked on the optoelectronics, energy, and the nanomaterial biomedical. That is the three very important fields nowadays. Okay, probably you next year ask me to come again, then that kind of application might be changed, but the core technology cannot be changed. Okay, then our strategies, we carry on the interdisciplinary application oriented, but based on the basic academic research. So in our group, we usually apply 2P. One is a patent, the other is paper. Okay, once you got patent, then you got your chance to cooperate with company. But if you want to graduate, obviously you need a paper. So that's usually in my group. Our student will carry on 2P. Patent first, then paper. Okay, then I'm going to give you 3 parts separately. So first one is the light conversion to light. So as I explained to you, your mobile phone, you have a white light. So that means you have blue LED. Then we develop the phosphor that's based on the inorganic. So the composite based on the kind of yarn. Okay, that is a formulation. So once you have blue LED, you have blue light, and then you decide the yellow phosphor. So yellow phosphor is something like this. So if you look at it from your mobile phone, it's this part. Once you use turn on the LED and with the blue light, then you will decide the yellow phosphor. By mixing with blue and the yellow, then you are okay to get a white light. Okay, that's what we call light conversion to light. And the formula, as I said, the formulation is our most important one. So you see the phosphor is a so-called ECN3 amino 5 oxygen 12. That is the ECN amino garment. We gave the first letter YAG. So it's based on yarn. So this one we call it a house, just like we have a new house. Okay, so this is the structure of the house. So you see, just like a cubic. Okay, so aluminum oxide has a tetrahedral of the hydral arrangement. It's an anion. Cation is between 3 plus. So it's a cubic structure. So formulation, then you need an activator, because if you have house, you cannot get lighting, so you need to have a incandescent light. So then ECN3 plus substitute into the ECN side. Then we call this one activator, just like a light into the house. Okay, based on these 2 parts. So if you have a CRN3 plus activator, CRN3 plus have a 4F, 1 electron, 5D no electron. If you excite by the blue light, then this electron will come to the excited state, then release as a heat. From the further excited state S1 down to ground state, you can see the yellow light. So by mixing with the excitation of blue light and the emission of the yellow light from phosphor, then you can get the white light. Okay, so this is the theory of this. For the application, as you can see this. So this one is the Beijing Olympic Winter Game. For the open ceremony, so you can see the blue LED and also the white LED. Without developing this kind of phosphor converted LED, you cannot get this other light. Okay. Now you know the theory now. In Taiwan, you can do many things, but when you want to do the research, you should look at the industrial infrastructure. LED in Taiwan is one of the highest productivity in the world. But this LED, so cost for the phosphor is 20% as compared with the full cost of 1 LED. So it's quite important. And for the blue LED chip capacity, so the highest, even this LED invented from Japan, but it's only 27 for occupation. In Taiwan, it's the number one in the world, more than 33%. So that's why if you know this industrial frame structure, you cooperate with that, then that will be good for them. But so you see, we have a completely industrial chain from substrate, AP wafer, packaging, application. So you can see the AP wafer, AP star and LED star, they unify into one. It's the world's biggest LED company. But most of them, they can produce high quality of blue LED, but none of them can make a phosphor. So then we know there's a hole over there. So based on our core technology, we can do this. So with our developer, we develop this kind of phosphor, then we transfer to two industrial companies, China Grace and Qime. Then they can support the phosphor into the industry with our technology. Not only for that, we can directly correlate with industry directly. Not only in Taiwan for AD-Star, LED-Star, but Luminance in Shanghai, Mitsubishi in Japan, and Merck in Germany, we cooperate with them. Can help them develop new type of phosphor. So that is a trick to find out the target. Use your core technology for the real application. Then this one just to show you one of the example. So this we call it a nitride post, European 2+ activator. So that's we cooperated with Mitsubishi. So this one is a red color phosphor. So you see, if we have only yellow color, you only can get a cool white. So we call this one a cool white. But can you get warm white, like the conventional yellow light? So then you mix with red phosphor. So we use this. So this one is the formulation. We cooperatively developed by Mitsubishi Chemical. With this formula, then so it's a red emission, red light emission. Then we can from the color change to cool white to warm white. So with this, we can find a pattern joining with Mitsubishi. Not only for that, with the characterization, as I said, formulation and synthesis. Once you synthesize this, you need to do the analysis. Then we use a single zone radiation to determine the valence of European. Then we use other dimension, just like Raman or others. We are allowed to know the mechanism. So that's why the first author in his life, the first paper published in JEX. Not only in JEX, also Mitsubishi can get the patent for real application. That is an example by using our core technology into the real application. Then we hear from industry. Industry say, oh, that's good. So you have red phosphor, okay? But this red phosphor, full width half maximum is too wide. So it's more than 100 nanometer. Then they said, you should narrow down this full width half maximum of the conventional red color, because this wavelength about 700, that's infrared, use this color. And the more narrow band, the luminescence intensity can increase. So they do the theoretical calculation. If full width half maximum can reduce from 110 to 30, the light intensity can increase 20%. So we always use companies' needs as our student working goal. Okay, so then we founded with your chairman Lee. When he stayed in my lab, we joined with a team in China. So we found this one fluoride as a host. One is 4+, so we really can get a nano band. Okay, so we can get a pattern and we can get the real product. So this fluoride is very good. Nowadays, people use this one because nano band. But they have a drawback. So you see, fluoride is moisture sensitive. Again, industrial complaint. We cannot use it smoothly. Then I told our network. So if raining, how can you deal with that? You put a raincoat. Then you put a raincoat for this phosphor. So we put a raincoat, we just put the alumina phosphate in the surface. With this, we can increase stability for 30 days from the 60% to 90%. So you always use the company's needs as your goal, put it in your target. Then you can publish the paper. Not only for that, you can get a patent for your application. So this one also published in English. Okay? But the student may tell you, Professor, I cannot do it. But it's very easy answer. Usually let he or him know. If you don't get it, you cannot graduate smoothly. Then that's very good work. They are easily accomplish the goal with the company. Okay. Then I move on to another topic. After visible light and the visible phosphor, already many people were on this field. Then they say, oh, the phosphor was dead. You cannot do anything more. But you know, the God always will help you when you hopeless. So then we come to the infrared. Not so many people work on infrared. And how can we deal with this? So infrared, we can divide the regime as infrared regime 1 with a wavelength from 700 to 900. Then infrared regime 2 from 1000 to 1700. Then infrared regime 3 from 700 to 1300. Okay, there's 3 regimes for biological window. Then for the conventional infrared LED, so you have a camera, remote control, they're all infrared LED. You can see with the emission of 810, that's usually for iris recognition. And with a wavelength of 850, so that is for the face recognition or night vision. During the night, you see the camera, that is an infrared camera. And also 940, so that is a blood oxygen detection for remote control. But most of the LED, they are very narrow band. So you see the full width maximum less than 50. Then the year of 2017, the company called Osram, they found an interesting phosphor. They use a blue LED excited with the phosphor that can emit a broad band of infrared. But nobody knows what is the recipe of that by that time. We only can see, oh, that is a yellow color. But with your knowledge of chemistry, you know the green color outside. The green color means something related with chrome. Okay? Then, if you don't have if you have this LED, you can use as a light source, replace with a conventional halogen lamp. Okay? Then you have used an infrared machine that's very big, at least occupy one table. But with this, you can shrinkage into small LED. Okay, so that is the product made by Osram. Then this is a film for you. So you see there's 3 mouse, okay? 2 small, 1 big. They see the peanuts. Then they want to eat these peanuts. But the slender ones, they worry about making it fat. Then they see how many calories. They say, oh, calories too high. Don't eat this peanut. Give it to fat one. Okay? Then the fat one wants to eat this. But in the sky, there is a big one wants to fight it. Then the smaller one can jump into the small hole, but big one outside, dangerous. Right? Then you ask eagle to eat the peanut. But eagle says it's too small. I want to eat you. Then you show to the eagle how fat of it. 4,000. Okay? So it's, if this eagle eats this fat one, it might be getting fat, then he abandoned. So you can go to buy Huawei's mobile phone. They have this kind of function. But let's use an image only. they use image only. Okay, so that means you have 10 apple got the same data. But if you use infrared LED, then use a kind of area detector, then you can see different apple, different things. So next time, if we have these real products for your food, you can carefully check it. Okay, so you see, the company asks us, can we make this? Then you see there are narrow band for the conventional LED. So with our knowledge, then we are okay to make so many different kind of broadband emission. As I said, formulation very important, but that is our core technology. It is very easy for us to carry on. Okay, then you have the experience for the intravenous injection. If you are too fat, if just a born baby, you are very difficult to find out your intravenous. But how can you deal with that? So we give a suggestion, irradiated by infrared, 940 and LED, different LED, but not so clear. Then if you use a broadband phosphor excited by blue LED, so you can see very clearly as compared with the others. So that is application. Then for future, if you go to hospital, don't be surprised. Robots will take a blood by this infrared LED automatically. Okay, because this machine can be available by chip, and they can recognize your invasive blood because of the infrared. Can easily detect by infrared. Then they can take your blood out automatically. So it means a new product always will change your life. Okay, just 1 minute. They can automatically take your blood out. You don't need to worry too much. So with this kind of achievement, our first paper published on this field was highly cited. More than 300 people take a reference of this. So for this reason, last year we got the National Synchrotron Center Outstanding Paper Award. Okay, so with this. So actually, the first author is from here. From this university, joint research with us. Okay, he found this recipe very important. Okay, so not only for that, for the real products, for the application, and we got the Tech Innovation Excellence Award as well from National Science Council. And then you can see the scale. So now the LED comes from the normal size. One chip more than 200 micro. If we down to the mini, down to micro, less than 100. Can you have an infrared phosphor to do it? Because normally, organic phosphor with the size more than 100 meters, micrometers. How can we syncate the size? Then again, it's a synthesis technology. So we use a template of the mesoporous silicon. Because mesoporous, we put it into solution. Then you grow the nanophosphor into this hole. Okay, so you can see each particle is about 50 nanometer. Then the phosphor is in the nanometer size. With this, you are okay to put that into the micro LED. So then this is the one we make the first in the world for application for the mini LED with emission of the infrared. Okay, so then the efficiency also can up to 90%. Because usually the particle size smaller, efficiency cannot be more than 10%. So we can push it up to 90%. Then for the future application, not only for the application for the conventional one, but for many new medical applications can make it possible. And then I shift to another topic, to the quantum dot. So nowadays all the display with a resolution about 4K. For the future, or we already approach to 8K. How can we do this? For the conventional display, we use a liquid crystal with a green and the red and the blue color. We call this triangle area is a so-called NTSC. NTSC data for the conventional LCD is around 80 to 90%. But now you use the iPhone, use the OLED, so that is bigger area, so it's about 100%. How can we make your display more attractive? Okay, then you need to increase this NTSC. Then you see, if you use a quantum dot film, excited by the blue LED, and up to this data is about 130. But if you use quantum dot as an emissive layer, then so this one is electroluminescence, this one is photoluminescence. By using the electroluminescence, you get up to about 140. Okay, so then you can see how good our quantum dot. And why can give this a large area? Because nanoband. Okay, because organic LED material is a full without maximum about 100 nanometer. But by using this quantum dot, it can less than 50 nanometer. So quantum dot becomes very important. For your research, you always need to pump into the essential material for the future application. Okay, so then obviously this topic also got the Nobel Prize in chemistry. So then you know the quantum dot has a cadmium containing ones and the non-toxic indium one, but this one is too toxic. This one is too expensive for indium and less brighter. So for our study, we use just residing in the middle. That is the quantum dot of perovskite material. By using this, because this perovskite material with absorption of blue light, so as compared with the conventional cadmium one, indium one, so this one is the highest. So with this, as I said, you always need to choose a material that have a very specific property, cannot compete with others. Then you work it on, then you got the chance for the real application. So we choose perovskite quantum dot with a higher absorption of the blue light. So with this, then again, if you have formulation, then you come to synthesis. Conventional synthesis of these quantum dots, they use one batch by batch, one power synthesis, one bottle. The uniformity between each bottle is not so good. Okay? Then in our lab, we use a microfluidic, continual flow of the material. So then this is the design. For example, we want to synthesize cesium lead bromide, so we use a cesium oleate and lead bromide. So this one dissolve first, mix with lead bromide, then they add the solvent. By mixing, then we can continually get the flow out of the quantum dot. Then the batch to batch is uniform and also with a large quantity. So you see this original two bottle and the final flow like this. Now we can make a red and also green quantum dot with the efficiency more than 90%. Not only for this, we also transfer this technology to this internal company. Now they can use our technology to make a large quantity. Then for another application, so you need to use the injection method. Then you can do as an ink for the injection. So this one is the ink head, so you can see the ink come out. Then this one is our logo by the inkjet printer, and that put it in the mini LED. So not only for this, we also cooperated with the Industrial Technology Research Institute. Now we can even make for a micro LED with a uniform dot. Okay, so once you have a very good publication, good application, then how can you increase your cited number? You need to write a review article. So this is our review article with a highly cited. So how important is this kind of quantum dot? Okay. Then we even have a very good one in chemical review. We give all our story, so we started with the high brightness of phosphor, then we need to have a higher stability, and then we need a nano band, then we come to the broadband of infrared, then we come to the quantum dot. With this whole story, you are allowed to get a very good review paper. So this paper is very, very highly cited in this field. Every day I receive a report, many people cited this paper. Okay? Then not only for the review paper, you need to publish a book. So this one is a phosphor handbook, is a kind of Bible for the study of phosphor. Not only for this, we extend to another 2 volumes with another Professor Xiaojun from the US. Okay, so remember how to increase your scientific visibility. You need to have a good quality of paper, cooperative with industry. Then you should have a review paper. Then you should have a book. Okay. Then I move to the second topic, light conversion to electricity. So as I told you, we develop a material for water splitting, split water into hydrogen and oxygen. Then we have a fuel cell, have electricity. Then we can store in all solid-state lithium battery. Then we also, because the lithium battery have a heavy cathode material, we remove cathode out. We put the oxygen in, so that will be lighter. Okay, that's for future metal air battery. Then because now energy is an important issue. Now per year is about 15 terawatt. That's usually the political energy from oil, gas, and coal. Renewable energy is important. So now in Taiwan, we expect that this year should be about 20%. But now we only up to about half, 10%. So that is largely behind our expected schedule. So then we need renewable, for example, wind power, that's solar power, or hydrogen energy. Then how can we, for the hydrogen, for the fuel cell, we need a clean of the hydrogen as a resources. Because this one is a fuel cell, you need an injection of hydrogen and oxygen. But if you generate hydrogen by using the hydrolysis or electrolysis, you need the electricity. That kind of hydrogen, we don't call it a green hydrogen. But use the water splitting, we learn from the photosynthesis. Photosynthesis can, the plant can absorb the solar energy, convert the carbon dioxide and the water into sugar and oxygen. So we learn from this, from nature, so we use our catalyst. Okay, then with the solar light, we can split the water into hydrogen. So this hydrogen don't need have any electricity. We call this one the green hydrogen. So with this, so we have the theory is like this. So we have a semiconductor band gap material. If we absorb the solar light, we can emit, we can get the electron from the cathode to anode. Then we can split the water to hydrogen. Okay, then the other side we can get oxygen. So that is a simple theory. You need the material with the semiconductor behavior. What kind of material is the best one? Actually, silicon with very high efficiency. Then we use a silicon rod. Okay, then we put a cadmium cyanide as a catalyst. Then we can dump it with a world record efficiency in the year of 2015. So we can get this kind of data, approach the world record by that time. So then, after 10 years later, in the year of 2021, we even write a review paper for this. As I said, you have a very good quality of paper, then several years later, you should have a review paper. Then you should have a book, right? This is a book we publish. Okay, then I give you to another example why cold technology is important. As I said, garnet structure can as a material for phosphor, yeah. But this also can as a same structure, but with a different formula. Lithium, and titanium oxide, then can as a solid state electrolyte. For the conventional battery, you have a liquid electrolyte in the middle. So this one is an air sensitive. Then that's very easy to explosive. How can we prevent this? So this topic also got the Nobel Prize. So many of our study related to Nobel Prize at the end. Then this one is a conventional liquid one. So electrolyte is liquid, it's an organic one, flammable. So during the car accident, you have no chance to get rid of it. Very dangerous. So that's why even now I work on battery, but I'm harder to buy the automobile electrical car. I cannot trust it too much. Dangerous. But if you use our solid state electrolyte, that's all solid state. So it's very safe and even longer life. So with this, I think nowadays the people said the energy density should be up to 300 watt-hour per kilogram. But for the year of 2030, they should up to 500 watt-hour per kilogram. By using the conventional liquid one, cannot approach this goal. It's only solid state battery can give us a chance. That's why this kind of research becomes very essential. What kind of material can do this? So you see the conventional liquid one with a conductivity up to 10 to minus 2. But with the sulfur content can up to this data. But the sulfur is dangerous. When explosive, they can release H2S. That's even dangerous. So that's why this material controlled by Toyota. Up to now, they cannot use it for free. For our study, we use oxide material. Okay? Even a little bit less, but that's more safe. So the material is just like, as we said, garnet as well. And lithium in between. Lithium in between can have a lithium channel for conductor lithium ion in between of cathode and anode. So then, conventional one, the middle part is the liquid electrolyte, but we change to solid electrolyte. So then we can do charge and discharge like a liquid one. So then, up to now, we are the leading study of this. Then we have chance collaborate with China Oil, and the Phoenix Battery, and the Foxconn company, and the Formosa company. So they claim they are the leading company, but we claim we are the leading lab to leading them for the future. Okay. Then we move on to the other topic. If you have solid state battery, you still keep a 500 watt-hour per kilogram. It's not good. How can we extend that? Then we just compare with lithium air battery with conventional lithium battery. So can about 3 times the capacity of that. Why? Because you have cathode material. You just take it out, you put oxygen in. It should be lighter and cheaper. Okay? Then on that we can do this. For example, for lithium air battery, we just remove the cathode, lithium cobalt oxide, lithium iron phosphate, we remove it out. We put oxygen in only. Electrolyte is the same. As I said, we use a solid state electrolyte. Then we just put a thin metal layer here. After you make this battery, you can do release energy. So discharge, you can get lithium peroxide here. Then charge, you can do the reverse chemical reaction. Then again, as I said, the formula and also the targeting is important. For our study, we don't use a lithium air battery. We go on the sodium carbon dioxide battery because lithium is a limited material. For our study, we use a sodium replace lithium and carbon dioxide replace oxygen because carbon dioxide usually people don't like it. We use it as a resource. So then for our study, we use this one to carry on. Okay, so we have the sodium metal and the solid state electrolyte, and then we use a ruthenium carbon nanotube as a catalyst. Then we inject the carbon dioxide in. Then they can form the sodium carbon dioxide. Then they can have a reverse chemical reaction. So with this, we are okay to do the discharge and the charge. with a very high, 3 times higher than lithium battery. So that's why we can easily publish in high quality of journal. So with this, you think that can be used in Earth? Definitely yes. But how about Mars? Okay, you think crazy, you want to go to Mars. Elon Musk wants to go to Mars. Because Mars has 95% carbon dioxide, then with our battery, we can put it, then they can generate as a source of carbon dioxide. So in the year 2033, not only USA, but also China, they're going to landing the Mars to start the human life over there. But by that time, we think our sodium carbon dioxide battery might be very useful. So then, as I said, you have very good paper, then you should try very good review. So we have a very good review, chemical review, for talking about this metal carbon dioxide battery. Then we also cooperated with companies. Not only for that, we got the Tech Innovation Excellence Award in the year 2021. Then you will ask me, for the year 2030, nowadays we use a liquid lithium battery. In the year 2030, you will use solid state battery. But how about 2050? I guess should use a metal air battery. So as you expect it like this. So can your car fly? So this car was set up in China. They just make it fly for half hours with a conventional lithium battery. They use a lithium battery and let this kind of car fly for 30 minutes. For my dreams, we should use a metal air battery, make it a longer time in the sky. Okay, then for my dream, the people have the same dream like me, Japanese. Japanese do this. They say metal air batteries for future transportation, make a car fly. Okay, so this is my second topic. Now I move to the third topic. So that is nanomaterials. So if you have nano gold, so you will absorb the green light. Then you have plasmonic effect, can induce heat. But how can you absorb the infrared? Because infrared can absorb by the human body with a deeper layers. Then if we can design the gold nanoparticle with a length more from the lengthen part, you can see the higher the infrared wavelengths can approach. Then for our study, we use for the mouth cancer cell, then we have a gold nanoparticle, but with a sharper part. The sharper part, because we designed to absorb the infrared, then can generate the heat. So this one is a mouth cancer. Then we call this one if we put this star-shaped gold nanoparticle into the mouth cancer cell, then excited by the infrared, then we can, because the human body is a window around 700 to 900 nanometer. With this window, then we use the infrared can penetrate to our mouth, then absorbed by the nanoparticle star-shape. Okay, then we try for the real case. So this one is the oral cancer cell. So you can see, and then we use fluorescence material in combination of gold nanoparticle. So you can see they can really get into the cancer cell. But it's only excited by the 1.8 watt per centimeter for 1 minute infrared. So then all the cancer cells die. Because cancer cell die can get a color by treatment blue. So it's only 1 minute, cancer cell will be dead for this. So then nowadays it's not only for this one, we also develop the nano bubble. Okay, with a kind of nanomedicine inside of this bubble. If we can put it into the brain, then we excite by the ultrasonic. Ultrasonic will destroy the bubble and make it explosive. Then can easily let the material get into our brain. Okay. Then this is our study based on kind of concept. Okay. So now we are not only working the inverse regime 1 and 2 and 3. Higher the longer wavelength, the higher the penetration depth can obtain. So this is our study. So now I think nearly the time of my talk. So today I'm going to let you know how important of the core technology. By using of the formulation and synthesis and the analysis and also the application, then we work there for the light conversion to light. That's for optoelectronic material. Light conversion to energy. Okay, light conversion to the biomedical one. Okay, so then I hope you have some idea for this. So at the end, also ChatGPT helped me draw this kind of figures for YouTube. So then this is the end of my study. At the end, I would like to thank Professor, also now is the Chairman Lin. He contributed a lot for this kind of topic when he was a PhD in my group. Then I also appreciate all the group members who stay in my group, who contribute to this topic. And at the end, I would like to thank all the audience for your listening. And I hope this kind of talk will make you interested for the sciences. So thank you for your attention.